Okay, so here's a thought. What if I told you that one of the oldest predators out there, crocodiles, are actually using like complex physics, Newtonian mechanics, geometry?
You'd probably get some funny looks, yeah.
Yeah.
People tend to think of them as, just primal instinct. Big teeth, big snap.
Right, just pure reaction. But the evidence, well, it suggests something else entirely, something much more sophisticated going on under the surface, literally.
It really does. When you actually break down how they hunt, it's less about simple instinct and, well, it looks a lot more like applied physics and maybe even unconscious calculation.
And that's exactly what we're diving into today, how these crocodiles are using these principles, calculation, physics to be incredibly efficient hunters. I'm not saying they're, doing math problems with a pencil.
No, definitely not. But evolution seems to have hardwired them to solve these complex real-world problems using physical laws with amazing precision.
It's fascinating. Survival in that swampy environment has basically forced them to become these natural optimization machines. Their whole hunting method relies on executing actions that, well, if you analyze them, they map onto math equations, solved on the fly.
Yeah, solved in real time. It's pretty incredible.
Exactly. So for you listening, we're going on a deep dive. We're going to unpack the source material and look at 4 specific kind of integrated ways these stealth masters use calculation and physics. We're breaking down their hunt into, well, almost a science.
Okay, sounds good. Where do we start?
Let's start with the absolute foundation of their success. That's silent stealth. And this really hinges on mastering buoyancy physics. They're basically living submarine controllers.
That precision is key, isn't it? To get that almost invisible float, they have to manipulate their own body mass relative to the water and do it instantly.
The mechanism sounds simple on paper, just regulating air in their lungs. But the level of control needed to do that perfectly, moment by moment without making a single ripple, that's immense.
Right. They're not just like holding their breath underwater. They're actively fine-tuning their density.
How exactly?
Well, think about a scuba diver, right? They use a BCD, a buoyancy control device, fiddling with air to stay neutral. The croc does this internally. Its lungs act like these complex pressure chambers.
Okay.
So they're constantly running this sort of balance equation in their bodies, adjusting just enough so only the bare minimum, usually just the eyes and nostrils, breaks the surface, minimizing that surface tension disturbance.
Like this perfect balancing act. Minimize exposure, stay stable against currents, or even their own tiny movements.
Yeah.
Because if they mess up, even slightly.
Oh, weight gives them away. Yeah. The surprise is gone. Lost meal.
So that precision is absolutely non-negotiable. It's instantaneous physics, regulating displacement versus mass for near-perfect invisibility.
It's a beautiful living example of density calculation, really.
Okay, so they've achieved that perfect silent trim. Stealth. Check. What's next?
The attack itself, right? That must involve a whole different calculation. Totally different. Now it shifts into ballistics and kinetics. How do you launch from that perfectly still position and guarantee an intercept?
Right, this is where the geometry comes in. Calculating distance, velocity, the strike angle. But surely they're factoring in more than just where the prey is at that moment.
Oh, absolutely. This is where it gets really clever. It's the difference between just lunging at a spot and, like you said, solving a complex interception problem. To make sure that strike connects, the croc needs to analyze 2 critical, constantly changing inputs at the same time.
Okay, what are they?
First, the speed of the water flow around it. If it's in a river, that current is a big factor. It affects the launch, maybe even the prey's path.
Makes sense.
And second?
Second, the precise vector, the direction and speed of the prey's movement.
Okay, let me just push back a tiny bit here. Is that really analyzing velocity? Or is it more like, highly refined instinct based on watching things move a lot? That's a fair question, and the distinction, according to the sources, seems to be in the predictive correction. Their brain processes this data almost like a guided missile system. It's aiming for the meeting point, not just the current location.
How does it get the data?
Well, they have these specialized pressure sensors along their jaws, on their skin, super sensitive. They can apparently detect tiny shifts in water pressure, which helps them gauge the current. And then visually, they're tracking the target's vector.
Wow, okay, so they're factoring in the water's movement and the target's movement, which means they have to project where the prey will be, considering its speed and any push from the current.
Precisely. They're essentially solving for T, the moment of interception, and calculating the launch angle and the power needed so their jaws snap shut at that exact predicted spot.
It's all about efficiency, millennia of evolution honing this. Because a slightly off angle means wasted energy, maybe a lost meal, critical.
Absolutely critical.
Which, actually, that brings us perfectly to the next layer.
Yeah.
Because the geometry, the angle, it's useless without perfect timing. If geometry is the how and where, timing is the when.
Yes. And this is where that famous crocodile patience really comes into play. It's not just sitting there. It's actually part of the calculation process. That stillness is active data collection.
We see them, absolutely motionless for ages, minutes, sometimes hours. They aren't just napping by the riverbank.
Not at all. They're observing, they're updating the variables, the brain is measuring the prey's speed, maybe its patterns of movement over time, and it uses that accumulated data to predict the exact second and the exact position where that prey will be most vulnerable.
Vulnerable meaning.
Often when it stops, like maybe lowering its head to drink, that predictable stationary moment.
Okay, let's break down that prediction bit. If it's waiting, say, an hour, it's watching patterns, right? Like a pattern recognition task. Waiting for things to stabilize or become predictable enough before it commits.
That seems to be the key. It's like this extended risk-reward analysis. Waiting longer lowers the risk of a rushed, failed attack. The longer they observe, the more data points they have, the better the prediction of that perfect, vulnerable moment. They're not just seeing speed, they might be gauging acceleration, deceleration too.
Yeah, and using that to extrapolate where the target will be and when. Okay.
Yeah, exactly. So they're essentially using elapsed time itself as a variable in their attack projection model. The patience isn't just patience. It's the time needed to get the highest possible confidence score for the kill.
That totally changes how you view that classic image, doesn't it? The croc just sitting there, it's not passive waiting. It's a high-stakes stakeout with constant mental updates.
It's pure, low-energy data gathering combined with really precise predictive power. Their whole strategy, surprise, overwhelming force, it only works if that timing calculation is basically flawless. They weaponize time.
Wow, okay. Stakeout armed with the projection model. I like that.
Yeah.
Now, there's one more piece. Perhaps the weirdest bit of applied physics they use, something they actually ingest, a physical tool to help with all this. We have to talk about the rock trick.
Ah, yes, the gastroliths. It always surprises people, doesn't it? The fact that crocodiles deliberately swallow large stones.
Yeah, you hear about it and you think, did it just swallow that by accident? But no.
No, it's intentional, and it's not for digestion, not like grit for birds. It serves a very specific physical function.
Okay, so if you see a croc gulping down rocks, what's the physics benefit? Especially thinking about the stealth and stability we just talked about.
Those rocks, the gastroliths, they act as ballast weights. That's the key. They help the crocodile actively manage its mass distribution, its center of gravity.
Ballast weights. Okay, that immediately makes me think of submarines again.
Yeah.
Or ships.
It's a perfect analogy. Subs use ballast tanks, flooding or emptying them to control depth and trim how they sit in the water. The crocodile achieves something similar by adding dense, heavy stones to its stomach, sometimes quite large ones, several pounds.
So what does that achieve?
It effectively lowers its center of gravity, which has a couple of main benefits. First, it can help them dive deeper, maybe counteract some of that natural buoyancy if they need to go after something lower down.
Right. Makes sense.
But maybe even more important for the ambush predator, the second benefit is stability. Lowering the center of gravity makes them much more stable in the water, especially during that long, motionless waiting period.
Ah, so it helps them maintain that perfect, unnerving balance with less effort.
Exactly. It minimizes the tiny corrections they might otherwise need to make to stay perfectly still. The gastroliths help them achieve and hold that perfect trim underwater.
So the stealth segment, the buoyancy control with air, the geometry for the strike, it all connects to this physical tool, the rocks. They need the air control, they need the trajectory calculation, but none of it works if they're unstable bobbing around. The rocks anchor them.
Precisely. The stones provide that stable platform. They allow the croc to fine-tune its position just beneath the surface, defying its natural tendency to float too high, and ensuring that when the calculated moment comes, the launch is from a perfectly steady base. It's really elegant applied physics.
Okay, so stepping back, we started with this maybe kind of crazy idea that crocs are secret map and physics whizzes. And we've looked at these four connected systems that seem to, well, prove the point.
Yeah.
You've got the internal air control for buoyancy, the complex geometry for the strike angle,
Right.
the calculated predictive timing based on observation, and then this incredible physical tool, the ballast weights, the gastroliths.
Right. And what it all really underscores, I think, is how evolution is this incredible systems engineer. The survival tactics that really last, the ones that are super successful in nature, they aren't usually just random. They're often rooted in these fundamental, almost elegant physical laws.
Every successful hunt, every silent movement, it's like a calculation optimizing energy, maximizing efficiency.
They're not just reacting blindly to hunger. They are, in effect, solving equations involving speed, angle, mass, time, integrating all of it into one lethal, perfectly timed action.
It really is the ultimate expression of natural efficiency.
And maybe it leaves us with a question for you, the listener, to think about. If these incredibly effective survival strategies, from crocodile hunting to maybe the flight patterns of insects, that they're based on quantifiable mathematical physical principles, does that suggest something deeper?
Like what?
Well, does it maybe hint that efficiency, elegance, these kinds of principles, are they somehow inherent foundational properties of the universe itself reflected in successful life?
That's a fascinating thought to chew on. The crocodile isn't just some ancient reptile. It's like a living, breathing example of math and physics embedded deep in nature.